welcome to today's webinar, everybody. My name is Martin Atkins here at the
So welcome to today's webinar, everybody. My name is Saeed Ahmed here at the Energy Research Group at the University of Waterloo.
today
And today we'll be
pumps
talking about
and pump
pumps and pump
systems today.
systems again. And welcome for those to those who are joining us for the first time. And now welcome back to those who may have joined us in the past. Just remember
Just a reminder that these
these
webinars are
webinars are
sponsored by
sponsored by
Echo
Echo
Business,
Business and
and
that the
that
webinar today is going to be
it's being
recorded
recorded
and will be
and will be
available for
available for
viewing
viewing on
on the
Echo
Echo
Business
Business YouTube
YouTube
channel
channel, as well as
as
their
well as here
social
website.
media page where they have. Please do that for them, and then we'll have some fun. And some of it will be rather important.
You're looking at selecting a pump is understanding both the pump performance and characteristic and the system characteristic,
Characteristics as well.
as well
And
as
we'll
we're
briefly
going
talk
to
about
briefly talk about why so many pumps and
so
industrial
many
pumps are
pumps and
oversized and
industrial
how
pumps
we
are
can deal with some
oversized
of those.
and how we
I
can
will also talk about safety
deal with some of
factors
those.
and uncertainty
We'll also talk
and
about
how they play a role in
uncertainty, uncertainty for
oversizing.
example, and safety factors have on the operation of the pump between 20 to 30%.
Why we are interested in pump system, it's estimated that between 20 to 30% of industrial electricity demand is to do with pumping of some of form or another. And if we go around our process plant, there are lots of pumps, especially for large sites, that they may have several thousand pump system or individual pumps, so they soon add up to quite a large energy use. It's estimated, and certainly is my experience, that around 75% of our industrial pump are oversized. And you know that a large pump implication not only on energy but also on reliability, maintenance, and of those pump systems we have talked about a little bit about in the last pump webinar that we had earlier in this year are how operating a pump away from a special efficiency point can have a major negative effect on the pump performance and also the reliability of the pump because of the fluid dynamics that are occurring within the pump now. Also, we have to keep in mind that because we're dealing with a pump system and not just with an individual pump, the pump is only part of a wider system with a wider purposes. Then it's important that we look at pumping systems, that we actually consider the whole system, and that's really what we're going to be talking about today, is focusing on the system in matching the pump to the system. And just to reinforce the point, this is a good study from Finland across multiple industries, evaluated 1690 pump systems across 20 sites, average pump efficiency 40 less than 40%, 10% of pump less than 10%, average motor efficiency 81%. Major factors that affected pump performance: oversized pump, throttled valve, seal leakage, highest downtime cost. Pump and system. This won't be teaching you how to suck eggs, but it's important just to review what a pump curve and the information that we may find from a vendor when we look up and we're looking for a pump. Okay, so here is a pump curve for the pump on the right, and so what it does is it captures the performance of the pump at different, and it will go along the pump cube. We just look at the pump curve. It basically expresses the performance of the pump, how much flow rate the pump will generate at a given head. or a given pressure drop that it has to deliver. And the three curves there on the four curves, sorry, are four different impeller sizes. So it's very common to have a casing size and then having a size different and impeller size available for that. And that's each one of those curved lines show you the performance of each impeller size more recently with the new pump selection package. And that have online, you put in your requirement, it will actually give you a specific impeller diameter, and you know these can be machined down. The supplier will produce one to that given specification.
specification.
These other lines that cross our lines of constant pump efficiency, and so we can then use that to estimate what the pump efficiency we will be at a given point. And obviously there is a point on the pump curve where the efficiency is at a maximum. Now this other line, and this other line is also important as well, especially where we have application where we may have a variable flow rate. In our demand, there is a minimum flow rate that the pump needs for continuous operation without any major crisis. So sometimes that's not actually given on the pump curve, but it'll be given in the specification for the pump. There should be a recommendation of the minimum flow rate that the pump should be operated off. There's a bit above that flow rate. Okay, so if we have a given requirement, say for a certain flow rate, then we can look at what head the pump will produce if at that flow rate or vice versa. So you may know what pressure drop will be, and we're interested in what the flow rate will be at that certain point, and then we also have a pump efficiency, so we can then calculate the power requirement also too. Sometimes they're all on the one page. I just split them up. There will be a net positive suction head required, some information on that given for the pump, and in this particular case it's done away from the pump curve proper. And so here we have the MPSH required for the pump for the different impeller diameter and PSH for different pump diameters. So that's important information to have, because we also need to make sure that our system has a margin that it will have more positive suction head available than it's required by the pump. Otherwise, we are going to run into cavitation issues, as well as then often as there will be a power requirement as well as with a power consumption at a given operating point. So these are net required net positive suction head, and then for a given operating point we can then look at determine what the required in net positive suction head, also what the power consumption of that pump will be at that given operating point, who have had different impeller sizes often, or if you actually specify a impeller size and you're interested in variable speed, for example, then it's also important to know how the pump curve will operate under different operating speeds, so that this one of the pump that I have down in the lab, we specified the impeller sizes, and we are supplied with pump curve are different pump speeds in our pipe in pumps is connected to a variable speed drive. And so now we know the performance of that pump at different operating speeds, as well as that useful to know that's not provided there's some approximation that can be made using the affinity law.
Okay, so there we have our pump goes for the different other speeds. And in this case, those lines are constant lines of constant efficiency. Now, this is we talked about this in previous webinars, but it's useful to reinforce this point is that ideally pumps are designed to operate within a very narrow range continuously.
Pumps are designed to operate within a very narrow range continuously. They can
And
be
they can
operated
be
outside
operated
of that
outside of that
preferred operating
preferred
range
operating range
continuously, but there will
continuously,
be
but
not
there will be
some energy consequences, but
those
there will be some
energy
performance and some reliability
consequences.
consequences.
But those
And you have talked
performance
about those in the past, but if you're planning to operate
operating
outside
range
of that preferred
in
operating
terms
range
of operation,
continuously
then
for a
then
long period of, it's not the right pump. The flow rate at the best efficiency point, that's important to know, and there's an allowable operating range outside of that, but that's really only for short-term operation, okay? So we have talked it. Okay, so let's just briefly go through a pump system curve and how that's drive. So in this particular case, we have our pump and we have our system. We're just pumping liquid between two tanks, and there may be a heat exchanger in there for some reason, and there'll also be lengths of pipe. There'll
there'll be
there'll be
entrances
entrances
and
and
exits
exist
there'll be entrances and exits to
entrances and exits to process equipment. There
process
will be
equipment.
valves. There may
Now,
be changes in pipe size, the pipe diameter, which will then
pipe
have an
diameter
effect
will
on
then
the pressure
affect
drop as
the
well
pressure
as
drop
as well as
we need
so
to
we need to
understand
understand our pump
our pump
system,
system.
and so from that we can generate our
And so
pump curve, okay, and that pump curve essentially describes the pressure drop as a function of flow rate.
the pressure drop as a function of flow rate for that particular system. And so if there is a static or an elevation difference between our two tanks, for example, then there'll be a static head. So that the pump, if we have a closed, there is no static head difference, and so the inlet and connection of the head major components is what we call the pressure and South meter long pipe and your pump friction equipment, whatever made it in our overall system. If we are doing a design of a system,
If you're doing a design of a system to estimate what there will be, and there's some software that can help you do this, you can do this empirically by hand, and there are some different methods
there's some different methods, and
methods, and we will in the future look at it in more detail how we generate a pump system
and
curve so we can estimate whatever pressure loss versus empirically.
already.
There, just a reminder, our operating point of our pump will always be uh, a pump curve and a system curve intersect, okay, so you can't get around that. So you understand our system curve, if we want to size our pump, really what we are trying to do is make the operating point at the desired flow rate or head at the best efficiency point of the pump, and then if there's any changes in our system, then we want to be able to look at, well, in our pump curve. So we are going to spend a few minutes talking about what things we need to do or no specify in order to select a suitable pump, and then also to size it correctly as well. Match the pump to the system, analyze several pump sections, bad efficiency point, total cost, ownership, reliability analysis. System performance requirement, hydraulic requirement, pump characteristic. Pump selection, hydraulic aspect, system flow rate, static head, total dynamic head, net positive suction head, suction pressure, minimum flow rate, total working pressure, service hours, control method, liquid temperature, vapor pressure, viscosity, solid size, content, density, other characteristic.
The hydraulic aspects, then there is head requirement. What is the dynamic narrow margin? Total working pressure hours is the system control. We also know what our it's important uh, that curve is a highly viscous liquid that you're pumping, and its performance can be done, but you actually and all explosive seals that you make important liquid properties that we need. That's highly toxic. And
Then
seals
the seal that
select
you may select or the type of pump that may select may be different than just if you're just pumping water. Okay, so those are important liquid properties. Mechanical aspect, pump size, impeller diameter, efficiency, net positive suction head required, minimum pump flow speed, material of construction, operating environment, bearing, cooling, sealing requirement, coupling, safety protection requirements, minimum requirements. A lot of our motors operate at around 1500 RPM, but we may want to go to a higher speed pump. That's an important choice to take a look at. Two main parameters that are key to pump selection: total head, flow rate, static head, and dynamic head. Dynamic head usually the source of most uncertainty. Dynamic head, high friction bends and valves.
meters here, and then he generates this lovely system curve. And you'll notice that at the, so we've had three different flow rates here. We've got 100 cube per hour, which is actually the desired flow rate, expansion requirement, and then he's also at 140 cube. We've increased our flow rate requirement. Okay, so that's important requirement 33. Then we also select a pump we're aware of. Now, if we go ahead and we select a pump for the highest flow rate, then we also have to have as a head rate 33 meters of head. And so we will then throttle our, change the control valve to throttle the pump, and so we will achieve system curve. If we select this pump and we requirement is actually 100, then what will happen, we will then throttle control valve to throttle the pump, and so we will an hour, but then we will curve back, and because we're using a control valve in this case, what we're actually doing is altering the system curve by providing more pressure drop in order to reduce our flow rate, and so the pump will actually operate at 100 cubes per hour, and the total head delivered by the pump will be 40 meters. Okay, so if we just compare point A and point B, where we will actually operate is at point B. And so our head requirement, the head delivered by the pump will be 40%. Because we move away from our best efficiency point, efficiency is going to drop. So it may drop from, say, 80% at point A to 70%, altering the system. Pressure drop will actually operate drop, so it may drop from, say, 86% per hour, and the system curve that we had, then our head requirement was only 18 meters 6%. Sorry, kilowatts, 15.6 kilowatts. However, if we'd sized the pump initially for the 100 cube per hour and the system curve that we had, then our head requirement was only 18 meters. So this is this point C here. Okay, so we only needed had more certainty around this pump curve, or more faith, in the system curve, and not applied any safety margin, then we could have still picked a pump and operated at its best efficiency point, and we would only be consuming 6.1 kilowatts instead of the 15.6 at point B. Okay, so that's quite a difference in power consumption. The other thing to note is if we'd selected a larger pump, then we're operating outside of that ideal operating range, and so there would have been additional maintenance. So if we just follow that through in just the power cost, then the difference between that, if we take 8,000 hours a year and 10 cents per kilowatt hour, then the total power dollars per year is a large difference. That's more than double the operating cost per year just by that amount of open. Also, our motor will often be larger as well. And there'll be a capital cost implication as well. And as I mentioned just before, there'll be reliability increases. So original system curve.
Pump curve. Holy shit, bro. This is crazy. Avoid oversizing pump to begin with. Understand flow and head requirements. Select suitable flow method. Holy fuck, bro. Fucking bitch.